Hi, good morning, everybody. Welcome to another exciting, possibly rainy morning of organic chemistry. If you saw the radar, you saw a lot of the storms this morning. This dust went through Rockford and one is now going up to Wisconsin. And I am taking. Hi. Does anybody happen to, when you're walking to the parking lot, look at a car tire and say, wow, that's an addition polymer? That's also a thermoset polymer? Or do you happen to look at my water bottle and say that's a condensation polymer, that's a thermoplastic polymer? Or did you happen to look at vegetable oil and think, oh, that's a ester because it's a quantifiable lipid? All right, we're talking about carbohydrates. Those are molecules that are polyhydroxyaldehydes or ketones, or upon hydrolysis becomes polyhydroxyaldehydes and ketones. And yesterday I introduced the term of chirality. Chiral is the Greek word for handedness, and I found that was true this summer because I had two students in my Chem 1212 who were fluent in Greek. And I asked, is that really true? And they said yes. So I now know it's true, not just because I read it in the book. Everybody says it is in print. All right, now, talked about mirror images. Anybody do the homework? Take your hand and put it in front of a mirror and see the reflection. And that's a mirror image. And there are two types of mirror images. Those that are superimposable, where you can line it up and push two things together, and those that are non-superimposable, like your hands, because if I have my two fingers these, I can push them together and line it up, but nothing else lines up. Same thing with my feet. I have my shoes on, but trust me, if you don't, go home, put your one foot in front of the mirror, you'll see the other foot, and then take your feet and see, well, if I have the big toes line up, the rest of the toes don't line up. So they're non-superimposable. Now, once you know that definition for mirror images, you can come to, which I finished up yesterday, objects are either chiral or achiral. Chiral means they have a non-superimposable mirror image, they have handedness, or achiral, A means without. And that's an object that has a superimposable mirror image. And yesterday I showed you that my right hand is chiral. How do you know that? There's its mirror image, forget about the ring, and you can't superimpose it. And I also gave you the secret that if you ever see in something left or right, immediately because it has handedness, you know it's chiral. And we went through some examples. Is this a chiral object or not? Got a quick question for you. Did I do a car yesterday? The example is a car chiral. Did I do that? This is somebody. Anybody? Everybody. Raise your hand if I did a car.
Oh, no.
Okay, well in that case, and yesterday I did warn you, this time of the semester you find out that Dr. Webb should never, ever, ever think of going to art school. So, question is, 3 points. Is the following object chiral or achiral? And the question would be a car. Well, how do you do that? You look at the mirror image of a car. And here we have a car. Headlights, steering wheel, wheels, door, back wheels, tailpipe, rear headlight, rear lights. I told you I'm never going to art school. And if we do the mirror image, now it gets tricky. have the mirror image. Remember, this is a steering wheel, and even though it looks flat, a car is in 3 dimensions. The wheels are actually pointing down, and at the top you have the hood, and therefore you can't rotate this. Because if you were to rotate this to superimpose it, here the wheels are down, the wheels are up, and therefore you can only pick this up, and you see it's non-superimposable. So is a car chiral or achiral? Non-superimposable mirror image, it's chiral. And what's another way you can tell? You stand in front of the car with me, and I said, you're standing right next to me, and I said, once you get in on the left side, would you know which side to go to? The answer is yes, well that tells you it's chiral. Now, this reminds me of, if you've ever been to England, your steering wheel's on the opposite side. Thank God I never had to drive when I was in England. That would be challenging. Almost got killed twice in England crossing the street, because even though they say it, this was in Manchester, at every big intersection in Manchester, they have printed on the street warning, look the opposite way for American tourists. They don't say for American tourists. And one time I was about, you look this way because you think traffic, it's coming this way. I was about to do this, and a Bobby was right behind me, grabbed me like this and pulled me back. And first I thanked him for saving my life, which he did. And he said, sir, look at the ground there. It tells you which way to look. And then I finally found out how to cross streets safely in England. It's very simple. Find a little old man or lady, and when they step off and they're not getting hit, you can go too. It worked. All right. But we're talking about chemistry here, and therefore let's talk about atoms. And let's talk about chiral centers. And really, a chiral center is an atom in a molecule that has 4 different groups or atoms tetrahedrally bonded to it. And what we're really talking about is carbon atoms. And if you look, I have a model. It's carbon in the center, and notice I have red. Let's see if let's try something, do an experiment. You know, I have to do experiments. I've been doing it the whole semester with your brain. And now commercial. Is it easier to see it this way or this way? How many like the projector? Raise their hand. How many like me holding it up? Raise their hand. How many don't want to raise their hand? Raise their hand. Well, most of you didn't care, so the majority like this. You notice I have a carbon in the center here. Notice I'll never be a hand model. A silver tube coming up, black tube, yellow, red. 4 different groups. And this is a chiral center, chiral carbon. How do you know that? Well, if we look at the molecule, this is the importance of when you have a chiral carbon, it most likely is going to be chiral molecule. What's a chiral molecule? Something with non-superimposable mirror image. Here's my molecule, my mirror, there's the mirror image. And if I pick it up, which I can, and I go like this to superimpose it, go to silver, silver, black, oh, red and yellow don't mix. So let's do this. Now red and yellow are lined up, but black and silver aren't. So this is a mirror image, but as you saw, it's non-superimposable. And that's the important part of learning about chiral carbons. Now, what this really means is, in a chiral carbon, to have a chiral carbon, you need 4 different groups or 4 different atoms or combination thereof. Let's take a look at some molecules, or a molecule. And the question is, circle the chiral carbons in the following. Well, how do you do that? Well, you look for a carbon that has to have 4 different groups or 4 different atoms or a combination. Now, let's use some common sense. Remember, Sid Shapiro always told me and taught me, which he was right, common sense is not common. And I did a Sid Shapiro voice there. I'm so lucky to get to know him. And if a carbon has 2 or more of the same atom or group, it can't be chiral. So you can kick it out of the choices. 3 hydrogens, that can't be chiral. 2 hydrogens, that can't be. 3 hydrogens, that can't be. So all we have to look at are those 2 carbons. I'll say that again. When an atom, carbon atom, has 2 or more of the same atom or groups, it can't be chiral, and you can omit it from your choices. So 3 can't be, 2, 3 hydrogens. Now let's look at this carbon. It's got a hydrogen, a chlorine, a methyl group, and these 3 carbons I'll call R. Those are 4 different groups or atoms or combination. Therefore, that would be chiral. I look at this carbon. It's got a bromine hydroxyl group, which is different from a bromine, a methyl group, and I'll call this thing R or R prime. So it's got 4 different things attached to it. Therefore, that would be done. That would be, and I'm done. Now, since you have to have 4 different atoms or groups of atoms attached to a chiral carbon, if it's in a double or triple bond, either with carbons or oxygen, it can't be chiral. So I should share and let you have some fun. And why don't you circle the chiral carbons in the following molecule? And as I say here, circle the chiral carbons, 3 points each. And remember, chiral carbon has 4 different groups or atoms in it. And if a carbon doesn't have 4 different, it can't be chiral. I'll give you 3.75 seconds more. 0.2, 0.4, 0.6, 0.72. Done. All right, let's take a look at this. Which are the chiral carbons? Well, the easiest thing is to say which are not. Anything with 2 or more of the same group or atom can't be chiral. Oh, look, 3 hydrogens, that can't have 4 different groups. 2 hydrogens, that can't have 4 different groups. Any carbon in a double or triple bond can't be. Well, this is a double bond, both of those. That's how, oh look, carbonyl, carbon double bond to oxygen. Therefore, that's out. Therefore, we only have these 2 to consider. Let's consider. This carbon here, hydrogen, bromine, methyl, and I'll call this whole thing right here under my arm R. 4 different things. Chiral. I'll look at this carbon, hydrogen, thiol group. This whole thing under my arm I'll call R. These 2 carbons is different from these 4 carbons with the bromine. And therefore I'll call that R prime. R prime, hydrogen, thiol. 4 different groups. So those would be the 2 chiral carbons. Oh, this is fun. Let's do it again.
Quick question. Okay, so for that second carbon you circled,
Yeah.
did you circle the carbon or carbon and hydrogen?
We're only talking about carbons.
Okay.
If I circle the hydrogen, I made my circle too big like I did on the other one.
If, so for example, for the carbonyl carbon, since it's double bonded to oxygen, even if the H was an R group, it still wouldn't be chiral because
Let's
of the
do it.
2 bonds.
Nice thing about organic chemistry is why this, what will happen? Let's do it. Now, oh, I got 2 more carbons. 3 hydrogens, that's out. 2 hydrogens, that's out. This has R prime, and an oxygen. Is that 4 different things?
Okay.
No. And that's why if you have a double bond, you can't have it be chiral carbon. But if I look here, hydrogen, these 2 carbons and bromine, R. This carbon at double bond, everything else, R prime, hydrogen, how many? 3. You need 4 different atoms or groups of atoms. And both of you, thank you for your questions, all questions, good questions, my thoughts. All right, I'll explain more in a little while, but and I tell you, when I start writing carbohydrates, my hydrogens go down real bad. But anyways, this is called the Fisher projection of, in this case, glucose, which you do not have to know the structure of. But each intersection of the line is a carbon. Carbon there, 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 obviously there and there. And I'd ask the same question. Circle the chiral carbons in glucose. And I would put the structure, I wouldn't give you the name, because that would be cruel and unusual punishment, which is outlawed, at least at this point, by the Supreme Court. With the new justice, that may change next year. I hope not. Oh wait, I shouldn't bring politics into the classroom. And for tomorrow's lab, those that you haven't, let me remind you, the to-do list, the first line, you only need 5 lines, is conduct the experiments or the tests using dishwashing soap. Then the second one, conduct the tests using whatever, and so on. Also with this warm weather, as I said earlier this week and last week, remember, no spaghetti top, no open midriff, no shorts, no flip-flops, and no open-toed shoes. All right, let's take a look at this. If we look at this carbon, it's got 2 hydrogens, so it's immediately out. And let's look at this one. If you remember, I said that's an aldehyde, which really means this. So this carbon, which is this carbon, is double bonded to that oxygen, so that's out. Now, if I look at this carbon right here, hydrogen, hydroxy group, this carbon, the aldehyde, and these other 5, so they're all different, that's chiral. If I look at the next carbon, this hydrogen, this hydroxy group, these 2 carbons, and these 1, 2, 3 carbons, different, 1, 2, 3, 4, chiral. If I look at this carbon, hydrogen, hydroxyl group, these 3 carbons, and these 2, different, chiral. And finally, this carbon, hydrogen, hydroxyl group, the CH2OH, these 5 carbons, and that would be chiral. So glucose has not 1, 2, 3, but 4 chiral carbons. And something you will not see on my test, but This will not be on the test, mine are the ACS, but there are other isomers, molecules that are connected the same, stereoisomers, but their relationship in space are different. And the number of total isomers I could write with this kind of molecule with 4 chiral carbons is equal to 2 to the n, where n is the number of chiral carbons. When n is 4, if I did my math correctly, that's 16. There are 16 possible isomers. Another one would be, if I take this hydroxyl group and put it on there, the hydrogen there, that would be another isomer. There are 16 possible choices. Mother Nature only picked this one, which is amazing. And as I was talking about, this won't be on test, but you might hear the terms elsewhere, stereoisomerism or isomers. Those are isomers with the same molecular and structural formula, but differ in their orientation of the atoms in space. And I mentioned this is one isomer. If you replace the hydroxyl group and a hydrogen here, you get another stereoisomer, and their actual total of 16 possibilities you can draw by replacing which side the hydroxyl group and the hydrogens are on. And another way of saying it, isomers whose atoms are connected the same but different in arrangement in space. Again, this will never be on a test, but it's a term we use. I was the first person to identify and prove the existence of isomers. Someone, I don't know if you've ever heard this name, it's a French name, Pasteur, Louis Pasteur, and he was a great chemist. Not only one who did a lot of biology, but chemist. And it turns out tartaric acid exists in 2 forms, mirror images. And what did Louis Pasteur know or famous for? Using a microscope. And with a microscope, he separated one type of crystal from the other because the different crystals were mirror images also. That must have been a lot of work, with tweezers like that. And he was the first one to do that, have a sample of pure stereoisomer. When you have a mixture of isomers, that's called a racemic mixture, but as you notice, I don't even have a slide for that. And major structure, it's got to have a chiral center, and that chiral carbon, this won't be on the test, which is off, has rigidity. What that means, the rigidity, this carbon is locked in the tetrahedral when it's in a single bond. It's called sp3 hybridization. If I had nitrogen there that wasn't a quaternary ammonium salt, you could have it. Have you ever been in a windstorm with an umbrella and your umbrella goes whoop, and you get it back down and sometimes it goes whoop again? Well, nitrogen can go like that when it has non-bonding pairs of electrons, like in a primary, secondary, tertiary mean. All right, switches back on. There's a term you should be familiar with, and that's called enantiomers. And an enantiomer is a molecule with a non-superimposable mirror image. So, what's an enantiomer? Something that has a non-superimposable mirror image. And usually, since you have a molecule and a non-superimposable mirror image, you do the math, there are 2 things. They're called enantiomeric pairs. And if you look at here, I have mirror image, and these are enantiomeric pairs. Now, I always spell enantiomer, and I did it again. I always forget the N. somewhere in your future, if you see on a piece of paper, like with that, anybody else, because that's not the first time it happens, I keep emergency supply up here, so if you need
Okay,
some more.
thank you.
Why don't you pass these back? And you might see on a piece of paper I might hand out in class, draw the enantiomer of the following molecule, and you'd see that. And the question is, I want my 3 points, what do I do? And I want you to learn this, so that's why I'm doing this, is what this really means is draw the mirror image of the molecule. Because on my test, I had a teacher who was sneaky and did it. A molecule didn't have a non-superimposable mirror image, and the answer was, there isn't one. And I will never do that. If I ask you to do something, it will have an enantiomer. So what that really means is draw the mirror images. How do you do that? Well, I like to do for a mnemonic device to help my brain and memory, put in my mirror. You don't have to do this with a dotted line. And if I had my hand here, you'd see the reflection. What's closest to the mirror, you'll see first in the reflection. Well, first of all, you're going to have the same backbone. And achiral carbons, you don't have to worry about the mirror image because it's superimposable. So I can draw my aldehyde like that. If you wanted to draw it like this, that's okay. I don't. You don't have to. Either way, this is a true mirror image, but it's an achiral carbon. And at the same, if you look down here, you'll see an achiral carbon. So you don't have to draw it as the mirror image, which being an organic chemist, we're lazy. I don't have to do anything. I don't, so I don't. But now let's look at carbon number 2. What's closest to the mirror? Hydroxyl group. That's what you'll see in the reflection. First, what's farthest away? Hydrogen. Next one, what's closest to the mirror? Hydroxyl group. What's farthest away will be farthest away. Hydrogen. Ooh, this one, what's closest to the mirror, because that's what you're going to see the reflection first. Hydrogen. What's farthest away? A better looking hydroxyl group, and therefore it would be here. And finally, the last one, what's closest to the mirror? Hydroxyl group. What's farthest away? Hydrogen. And now I've drawn the enantiomer, which is another way of saying draw the mirror image. Now, one thing I'll warn you about Fisher projections, and I'll show you a slide in a little while. Fisher projections, the atoms or groups that are on the horizon this way are really coming out towards you. The ones that are vertical, this part, this one, are going away from you. Just like this. This is really coming toward you, but if you flatten it out, this would be like the hydrogen, hydroxyl, aldehyde, next carbon. Well, with a Fisher projection, you cannot rotate them because these are really out. And when I rotate them, these are going out. And when I rotate, the ones I rotate will go back behind the board and it wouldn't be superimposable. And therefore, with a Fisher projection, when you look, is it really the mirror image, which you won't do on my test, but in case you're wondering, is a question I've gotten from students. You can only pick it up and lay it over it. Notice that this carbon, hydrogen would be on this side, hydroxyl group is, so it's not superimposable. Now, before I let you have fun with one, quick commercial from the management meet. Remember, a week from this Thursday will be test number 4. That's also the deadline for the extra credit project if you were planning on doing it. It's totally optional. If you want, which I highly recommend, bring in your project well in advance for me to look at it. At that point, you don't have to type it out, print it, no types anymore. But anyways, I'll take a look at it. And one question one of your colleagues had yesterday, which was a good one at the end of the lab, is you notice you have to do 10 different molecules. They do not have to be all different functional groups. That's really too difficult. I've had students, 10 different molecules from different products, and they're all alcohols. That works for me. So all you have to do is, remember, there's a limit, only 3 molecules from a product, but they can be all the same functional group or different ones. They just have to be functional groups we talked about in class. All right. I'll let you try this one. Draw the enantiomer of the following molecule. 3.C. Oh, warning, real bad pun. Oh, it's so sweet. Everybody working with their sugars, carbohydrates. Wonder who's really good at pun. Looks like last carbon just went down. All right, let's take a look at this. Question is, draw the enantiomer of this molecule. Ooh, what should I do? Draw the mirror image. You don't have to, but I find it works for me. I put my mirror in and say, what am I going to see? The backbone. 3 there, carbon up there. What's an aldehyde? It's achiral. So I can draw it like that. Here I have, achiral carbon, so I could draw it like this. You could have put an HOCH2 the other way, but why would 2 extra work? Now, these are chiral carbons. What's close to the mirror? Hydrogen. What's farthest away? Hydroxyl group. And remember, your homework assignment, if you haven't done it, find a mirror somewhere. I'm sure there's some in the school, in the restrooms, because the men's rooms have on this floor mirror. And I'm assuming the women's restroom also probably has a mirror. And put your hand in front, or do it at home, and look at the mirror image. What's closest to the mirror, your palm, you'll see the reflection first. And next carbon, hydroxyl group is closest. Farthest away, hydrogen. Next carbon, hydrogen is closest, farthest away is hydroxyl group. And that's how you draw the enantiomer of this molecule. Now, switches off. I didn't mention stereochemistry and go into this when we're doing double bonds, but you can have molecules that are stereoisomers who are not mirror images. An example of that is a sister trans double bond. And they have a name for that, which I'll never ask, and the ACS doesn't. Those are called diastereomers. All right, switch is still off. We've been talking about Fischer projections. And Emil Fischer, who was a great German chemist, organic chemist, won the Nobel Prize for elucidating, meaning figuring out the structures of sugars and small carbohydrates, which side each hydroxyl group was on. It killed them too. I think, remember when we made the 2,4-dinitrophenylhydrazine derivative of ketones? Remember, it was nice and orange and you didn't have to isolate it? It's a way of making solids that you can get melting points and help identify. Well, he used that to do derivatives to help identify. Well, back then in the late 1800s, especially working with sugars, excuse me, organic chemists had a bad habit. Ooh, I wonder what that tastes like. Well, it turned out he didn't purify the stuff, and there was some 2,4-dinitrophenylhydrazine still in there, and he died quite young, younger than he should have, and later on someone had identified from, I don't know how they got his hairs or mustache hairs, the story goes, that they found out the cause of death was 2,4-dinitrophenylhydrazine poisoning. Don't taste chemicals when you're making stuff. All right, now, he came up with the idea of how do you show a sugar with its stereochemistry, sugar being a monosaccharide. And what he came up with is, for each carbon, it's tetrahedral. But if I rotate it and flatten it out, I'll draw it like this. And that's what he did. I used to have students have to do this on a test. I don't anymore. So you people in the back have everybody in front as witness. I said that. All right, switch is still off. There's a designation. If you work in a hospital and look at the bottle they used to feed patients intravenously, and I've been told this by a couple students of mine who are nurses, and we're coming back to get organic chemistry again to get their masters, because it's been too many years since they took organic and they were required to do that. And they were the ones who told me about this. But I knew the name, but I didn't realize it was on the actual bottles of the glucose. If you look at the Fisher projection, and you look at the highest chiral carbon, notice that this is an aldehyde, which is 1, 2, 3, 4, 5, 6 carbonyl. Carbon is always 1. It still works in here, even though we're using common names. This is the highest chiral carbon. That's not chiral. If the hydroxyl group is on the right, it's called D. If it's called on the left, it's called L. I assume that's for Latin for dextrose and levose, which is right and left. That's about the extent of my Latin, other than whatever I saw in the Roadrunner. But cartoons, I think there's Latin. And let me just take you out real quick to the real world. Again, it switches off. Have you noticed the name for glucose is D plus glucose? The D tells you the hydroxyl group is on the right of the highest chiral carbon. Now this is another form I'll teach you how to write glucose, but let's get back real quick. I want to get through this. I'm doing this because this might come up in your other classes and they'll say, didn't you learn organic chemistry? That's wrong. And I'm teaching you this now. This won't be on the test. We talk about enantiomers. You have enantiomeric pairs. They have the same physical properties, right and left, just like your hands work the same. But there's two differences. One is called optical activity, and the other is reactivity with other chiral molecules. Just like your right hand doesn't fit well in your left winter glove, especially if this doesn't. Same thing with molecules, how they interact. They only react with certain similar type of chiral molecules. And that's happening in your body. Again, greatest organic chemist, Mother Nature, set that up. And that's important. But let's look at optical activity. Again, switches off. Optical activity, that's a compound that rotates plane polarized light. If you look at this light, or if the sun was out, well, there is light coming through, but it's not bright. Light comes at you as waves. You know, light can be particles and waves. Let's think about waves. The light coming from that bulb, the waves are all 360 degrees around the compass coming at you. Now, plane polarized light is talking about where you only have one of those waves. How many of you have ever seen polarized sunglasses? And they're really good. They really dart reduce the sunlight coming into your eyes because they filter out all but one wave to get to your eyes. Well, chemists can do that, and they have instruments that you can measure by putting out one wave at this angle, and you put it through a solution, and the detector will say, is it rotated, and how many degrees, and is it rotated to, let's see, your right or your left. And because of that, optically active molecules in solution will rotate plane polarized light. If we rotate it to the right, you show in the name plus. If you rotate it to the left, you show minus. And if you saw it was D plus glucose, glucose rotates plane polarized light to the right. And at a certain temperature and concentration, that for pure material will always be the same angle, and that's a way of doing purity, just like you know temperature plus pure melting points to purity. This won't be on the test. All right, still have the switch off. A few terms that you might see in other classes. We have aldoses. Aldoses are monosaccharides that contains an aldehyde. Notice the very top aldehyde. And then we have ketoses. And what are those? Monosaccharides with a ketone. Notice the second carbon, carbonyl, carbon on top and below, ketone. Anybody ever hear of the term ketosis? People haven't gotten to that class yet in your studies. And that's a disease of the blood where you have too much sugar. What kind of sugar? Ketones. All right, a sugar is a general designation for either a mono or disaccharide. So therefore, glucose is a sugar, fructose is a sugar, and as I've told you, sucrose, which is two monosaccharides connect together, a disaccharide, is a sugar. All right, forget about the second structure. I'll get back to that tomorrow. Here we have D-glucose, which is still off, but I just thought I'd give you a few things. One, it's the most abundant sugar in all of nature, and we'll learn later on in this chapter why. It's the sugar in your blood that brings nourishment to your cells when it needs carbohydrates. It's an aldose hexose, aldehyde with hex, 6 carbons. And it turns out it rotates plane polarized light to the right. Again, switches off. Here we have D-fructose. It's a ketohectose, ketone, hex 6 carbons. It's the sweetest sugar per gram of any of the sugars in nature, which is why if you look at for the last number of years, certain foods like ketchup and other things, and especially children's food, they now have high fructose corn syrup. Because one, you don't need as much as sucrose because it's sweeter, and two, it's cheaper to make than sucrose. I'll talk later on, there's controversy for many years, does it cause certain things like Alzheimer's, not Alzheimer's, certain diseases or problems, and my personal opinion is no. I'll explain why later. It rotated plane polarized right to the left, as found in corn syrup, which they found a way of taking corn syrup, partially hydrolyzing it to make fructose, and that's why they call it high fructose corn syrup. And if you look at your bottle of pop, you'll see a lot of them use high fructose corn syrup. They used to, about 30, 40 years ago, use sucrose because they didn't know how to make high fructose corn syrup. It can be in a cyclic form. I'll come back to that. For those of you reading the book, there's something called the Hawthorne projection. It's a switches off two-dimensional way, this way, of drawing a three-dimensional structure showing stereochemistry. You can spend 2 weeks learning it, and you'll still have trouble. I know I saw students when I used to put on a test always get it wrong, and I said, why am I doing that? There are more important things I should talk about. So I cut that out. But you still, in case it comes up. All right, now it turns out a very important reaction occurs in monosaccharides, glucose and fructose. And I don't know if I'll get to it, but it's time for a little review. Remember Dr. White, me, I said no new general reactions. So let's go back and look at one. from test 2, you take an alcohol, react it with a ketone or aldehyde. When R prime is H, it's an aldehyde. When it's carbon, it's an alcohol. What you'll get is a hemiacetal. Now, it turns out glucose and fructose both have aldehyde or ketone. I have an aldehyde there, and in the same molecule, I have an alcohol, carbon with a hydroxyl group, and this can react together in that reaction. And based on the time I have left, I won't cover that now, I'll start that tomorrow. And if this reaction didn't occur, we wouldn't have any of the starches you learn to enjoy in our life with things like potato chips, rice, french fries. With that, on that, let me know, I will cover tomorrow.